Vectors in three dimensions. So what we're going to do here, we're going to look at this 3D a three-dimensional space, plot points, spheres, and planes in space, and analyze vectors in space. Well, so okay, number one. The right hand rule orientation. So that's something we're gonna look at later when we get to the cross product and when we get to other computations for applications of these three vectors in space. But well, what I would like you to see is how is the space formed. Number one, well, this is the XY plane that we have been working since pretty much our first mathematics class, right? However, now we're looking at this from a perspective. Otherwise, we would have looked at this from the top view, and that's going to be our X and Y plane, right? So here, the XY plane will be the floor of a solid. If we that later we will describe solids. Um, what do we have? So that's the xy plane. That's where z equals to 0. And then we have the xz plane. Xz plane. That is when y equals to 0. And lastly, this other wall having points in common on the x-axis and the z-axis. That is wait, that's it. That's the YZ. The YZ. Whoops, I'm erasing this. Okay. YZ plane. That is when x equals to 0. So, this is going to be very important later when we describe some of the surfaces, when we graph. Well, we're not going to graph in 3D a lot. We will only graph the easy ones too. The easy surface like planes, paraboloids, and other cylinders, you'll see. Okay, plotting points in space. We're not going to do them by hand. I'll show you why. So just real quick, we would need to have a good sense of perspective, or unless you have a good drawing class, but well, it's not a prerequisite for this class. So, okay, let's see. So that means I need to go 2 units in the x direction, 3 units in the y direction, and 5 units up. Alright, that means 2, 3, but I still need to count 1, 2, 3, 4, 5, and it's not going to line up with the 5 units here because of the perspective. So, I mean, even plotting sines, cosines, parabolas, radical functions in the Cartesian plane can be a pain. Now imagine plotting surfaces by plotting points. It's simply not a feasible task. So it's not something we're gonna do. So I mean, this is just a point that looks like any random point in the middle of nowhere, but I was trying my best to put it in the perspective. Okay, plotting planes in space. So to plot planes in space, x equals to 3 and z equals to 4, in the same way that you would draw like vertical lines or horizontal lines in the xy plane, we can plot vertical, well, not, I mean, depending on the perspective, these kind of planes. So here, I'm going to do x equals to 3, okay? So this wall right here, so x, y, z, this wall right here, which is the YZ plane, that's when x equals to 0. To have this x equals to 3, I would need to drag that wall along the x-axis 3 units. That is 1, 2, 3, and plot this plane like this. I mean, notice I'm just drawing like a square, like a rectangle. One thing to keep in mind here is that this plane extends forever. So it's not limited to just this square. It also extends to the negative octants up and down and goes on forever. So, but I'm just giving you a portion of the plane so you can see that is intersecting at x equals to 3. All right? Z equals to 4. This is well, in our perspective, this is going to look like a horizontal plane, but it's not quite. So in this case, we can't use horizontal or vertical because now we're taking in consideration all directions, and it's not just x and y. So x, y, and z. This will be what's that? Okay, so the floor actually. So the floor, which is z equals to 0, I need to drag that floor up 4 units to represent the plane z equals to 4. That means 1, 2, 3, 4. So I would need to go like this, like this, like this, and like this. But again, this is just a little portion of the plane. It's not the entire plane. This plane goes all the way back, all the way to the front, and all the way to the negative octants here as well. All right, so that just extends forever. Okay, so that's a little bit of what of how we plotting single values really represent walls or planes. So this is going to be important for later when we describe rectangular solids to find the volumes of them using double or triple integrals or their masses as well, or their surface areas. Formulas in space. Formulas in 3D space. Well, they're going to look exactly the same. The distance formula, the midpoint formula, the equation not of a circle, but that in this case a circle in space becomes a sphere. What are we going to do essentially? Simply add a z term for all of this. All right? So that's what we do in space for these same basic formulas. Of course, we're going to learn new well, not conics, but rather quadric surfaces in space. So putting all this together, find the equation of a sphere containing the points P, 0, 4, negative 3, and Q, 2, 1, 0. Well, actually, we're going to use these three formulas in the same problem. All right? Now, the question here is, well, so these points are the endpoints of the diameter. And in the same way that we needed a center and a radius to come up with the equation of a circle, it's going to be the same for the sphere. We need a center, which is ABC, and the radius is going to be the same, and our radius r squared. What can we do with these 2 points? Any ideas?
The PQ, like subtract them?
Subtract them.
Use the formula we used before?
Mm-hmm. Subtract. Well, in this case, we're not describing vectors, so we want to obtain the equation with the sphere. So again, we need a center and a radius for the sphere. So what can we do with these 2 points?
Use the midpoint formula to get the center.
That's going to give us the center, right? Because these 2 points represent the diameter, the length of the diameter, right? The endpoints. So using the midpoint formula, that's going to be, okay, so that is 0 plus 2 over 2, comma, 4 plus 1 over 2, and negative 3 plus 0 over 2. So the midpoint here will be 1, 5 halves, negative 3 halves. So that's the center of the sphere. Okay, so, but now we need to find the radius. How would we find the radius?
We have the center, so we can isolate it out in the equation next to it.
Mm-hmm. So that's one way, but that's going to give us a quadratic. No, but you're right. You're right. Any other ideas? There's a quicker way to get this. Any ideas? Yes.
Distance formula.
Distance formula between which one and what other point?
P and Q will create our diameter, so we can just use that
Mhm.
to get a radius.
Yep, and divide by 2. So another way is to find the distance between that center and any of the 2 points, but you don't want to work with these rational numbers and then square. You don't want to do that. So just find the distance between P and Q that is the square root of 2 minus 0 squared plus 1 minus 4 squared plus 0 minus negative 3. Careful, 0 minus negative 3. Well, anyway, this is going to get squared. So that's going to give us, okay, 2 squared that equals to 4. 1 minus 4, that's negative 3. Negative 3 squared, that equals to 9. And another 9. So 9 plus 9, that's 18 plus 4. Is that 22? Root of 22. But careful, because this square root of 22 is not the radius. It's the diameter. To get the radius, we would need 1/2 of the diameter. That is 1/2 times root of 22. Okay? Which is, I'm going to write it as square root of 22, everything over 2. I need it in this format better. So we're ready to write the equation of the sphere using the last equation in the definition box, where A is going to be, so this is going to be our, let me label, this is A, this is B, and this is C. So that'll be x minus 1 squared plus y minus 5/2 squared plus z minus minus, that equals to plus 3/2 squared, equal to the square of this number. Okay, let me square that number. That's root of 22 over 2 squared. That's going to give us 22/4, isn't it? Which reduces to 11/2. So that's the equation of our sphere. All right? That's the equation of a sphere. Okay. So that's a little fun and play with formulas that you know from algebra, intermediate algebra, just adding a third term, a third component to turn them into 3D, to turn them into space situations. And of course, now we're going to talk about vectors in space. What are we going to do? Just add a third component. If we had vectors A, B, now we're going to call them A, B, C. And that standard unit vector, if we had I and J in alphabetic order, we're just going to add the K vector. So, and now these standard unit vectors, instead of being simply 1, 0, now they're going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1 for the K vector. So, and the same properties we learned about vectors from section 13.1 are going to hold exactly the same. The magnitude of a vector in space is going to be the exact same magnitude distance formula. It's not going to change, but we're going to extend it to 3 dimensions by adding that third term. That's all it is going to be. Okay, given the 2 points, 2, -4, 6, and 0, -1, 3, let's write AB in both component form and as a linear combo of unit vector. That means AB, let's do simply terminal minus initial, 0 minus 2, that's -2, -1 minus -4, careful, that's +3, and 3 minus 6, that's -3. So that's a vector in space. In the same way, terminal minus initial, but we do it 3 times to represent a vector in space. And that equals, as a linear combo, that's a -2i plus 3j minus 3k. All right? So that's it's 2 answers in the same one. Finding the magnitude. Finding the magnitude of the vector, well, simply the same notation, double bars, AB. That's the square root of -2 squared plus 3 squared plus -3 squared. And that's going to give us, again, that's 22. Another 22, simply a root of 22. If we had a number, a perfect square, simplified, or any of the factors, well, this is simply 2 times 11. None of them are perfect squares, so just leave it. Okay, find the vector v with a hat that is a unit vector in the direction of A and B. Well, so what do we need for that? Well, v with a hat, which is the unit vector that is the given vector, AB, all right, divided by its magnitude. So the components of the vector we just got, that is -2, 3, and negative 3. Divide by the magnitude which we got in part B of the exercise. That is, divide by root of 22. Okay. And in this case, simply distribute or divide by root of 22 on the 3 component. That's a negative 2 over the square root of 22, 3 over square root of 22, and negative 3 over the square root of 22. Okay? All right, now a tricky part, and actually this is a very typical quiz and exam question. Find another vector, W, a vector in the same direction as AB, but it has a length of 3. Well, the initial given vector is not a unit vector. It's a vector of length root of 22. To solve a problem like this, first we need to come up with a unit vector. Once you get a unit vector, multiply by whatever number you want, in this case by 3, to ensure that vector has a magnitude of 3. So that means W is in the same direction as AB, that is, as a unit vector, and simply multiply by 3. That means this will be 3 times negative 2 over root of 22, comma 3 root of 22 over root of 22, and negative 3 over root of 22. Okay? And just multiply 3 times the numerators of these components, that is negative 6 over the square root of 22, 9 over the square root of 22, and negative 3 over the square root of 22. If you find this the magnitude of this vector, you will find that it's going to give you 3. Okay? We don't have to show this. Okay? We don't have to show this. Okay, so what's next? Okay, which one is that a negative? It's supposed to be a negative? Oh, the last one, right? Yeah, negative 9, right? Thank you. Okay. Well, I think. Nah, I wanted to do this. Okay, let me see if we get it. Okay, just give me a couple minutes. Okay, let's finish this in a few more minutes. Okay, I know we're almost out of time, but I would like to finish the section. Okay. So two vectors U and V are equal if their components are equal, and two vectors are parallel if there's some scalar, if they're multiples of one another. So this is the same idea as with vectors in 2D. So vector U has an initial point and a terminal point, and that's going to create the vector 2 minus 1, which is 1, 1 minus negative 2, careful, that's a 3, and 0 minus 3, that's negative 3. The question is V 3, 9, negative 9 parallel to U? Is it? Does that vector look like a multiple of this vector? So it is, because V equals to 3 times 1, 3, negative 3, which is indeed V equals to 3 times U. All right? So it's 3 times, and in this case it's going in the same direction. It's not going in the opposite direction like the previous problem we did in the previous section. Okay, so briefly, give me a couple minutes here. Okay, a plane is flying horizontally to the north, 30 miles per hour. Oh, I should have edited this problem, because plane flying at 30 miles per hour is definitely going to stall. So anyway, when it encounters a horizontal crosswind blowing west, okay, in a similar way we did before. However, there's a third force right here, which is a downdraft. That is, the airplane's going to push down, right? That's what's going to happen at 5 miles per hour. So let's use the vectors to represent the situation. So, well, unfortunately, I wouldn't be able to represent these vectors in space. So let's at least, wait, what happened? Okay, there you go. Let's represent this in 2D first. That is vector W and vector P. So if we were to represent the downdraft vector, if we put this in perspective, actually that downdraft vector would be stabbing the screen. Do you guys agree with this? Okay, so let's represent that. So P for the plane, W for the wind, which is going to the west, and D for downdraft. Let's represent this using vectors. So, okay, notice in this case, it's 0 in the x direction, 30 in the y direction, and 0 in the z direction. So, the wind, which is blowing to the west, that means, careful, it's going -10 in the x direction. So here direction, it's going to tell us the sign of the component. And 0, 0. And what's next? The downdraft is 0 for the first two components and -5 because it's going down, right? It's going down the vertical. And we'll also to find the, let's call V our resultant vector. So just add these three vectors together. There's nothing too crazy here. That's a -10, 30, -5. Okay? So find the speed of the plane relative to the ground. So now they're asking us for the magnitude of that velocity. Okay? The magnitude of V equals the square root of -10 squared plus 30 squared plus -5 squared. And that's going to give us a result of the square root of 1025. I don't have the result in decimals, but you can figure it out using a calculator. Now, I would like to notice in this case I went very easy with the wind vector and also the plane vector. So, because in this case it's going to the north and it's all going to the west. But what if? Okay. Side note. What if? Either plane or wind went to, or we're going to the southwest. What if the wind or the airplane were going to the southwest instead, and not just going simply to the north or the four cardinal points? So we would need to figure out the angle that represents the southwest. Isn't this the direction of southwest? Right? What's the angle related to southwest? (225). So I would need the trigonometric representation. 225. Oh wait, no. The magnitude, which is 30. Cosine 225. Sine 225. What if northwest?
135.
135, right? So same magnitude, P equals to 30, but cosine 135, sine 135. Oh, don't forget the degree symbol, right? That's because, on the quizzes, on the solutions to quizzes I will post on Canvas, you will see similar problems, but I have twisted the situation where we no longer go simply to the north or to the west. Over here, yes, I just say 30, but this is the same as saying 30 cosine 90, sine 90, and then 0 because the airplane is not ascending or descending. That's why I would represent the vector like this. But actually, simply I represent it as a 30 right here because it's going in the y direction only. And I think we can call it a day here.